Oxidation-reduction reactions, another type of reaction. Oxidation, reduction, so these reactions involve oxidation and reduction. This involves a transfer of electrons. So we get electrons moving from one reactant to the other reactant. These are also called redox reactions, which kind of looks like red ox, which reminds me of red box and makes me think, you know, my kids are going to watch a movie tonight. So, you know, we go off on these little tangents. Redox reactions. When we have oxygen as a reactant, chances are very good that that's going to be a redox reaction. Here we have iron reacting with oxygen. Basically, the iron is rusting, is what we would say, to form an iron oxide. This is a redox reaction. Here we have a combustion reaction of octane. That is a redox reaction. Here we have hydrogen gas and oxygen gas. Hydrogen gas combusting, and that is also a redox reaction. There are some reactions with oxygen that are not, but for the most part, they are redox reactions. Let's see what this next slide looks like. Well, there's an illustration. Here's a balloon that has hydrogen and oxygen gas together in it, and you bring a candle up to that, and it goes kaboom. Nice big explosion. Yeah. Like, man, why can't we do that, right? Here's an example of a redox reaction without oxygen. I'm going to go back here real quick. I want to look at, let's see, I want to look at this one. I can't write with an eraser. Let's look at this one. In that product, Fe2O3, what kind of a compound is that? It's ionic, right? So there's ions in there. What charge does the iron have? 3+. Oxide always has 2-. What we started out with was iron, the element. How does an iron atom become an iron ion? It loses electrons, right? How does an oxygen molecule, which is a neutral charge, how does that become an oxide ion? By gaining electrons. So in this one, we can very clearly see, yes, there's a transfer of electrons. The iron gave electrons to the oxygen. And that's what's occurring in all redox reactions. It's easiest to see when you have an ionic product. In these two examples, we don't have an ionic product, and so it's a little harder to just look at it and say, oh, yeah, I see electron transfer. Let's see where we are here. Here's an example of a redox reaction without oxygen. Here we have a metal reacting with a nonmetal. And generally when that happens, it's a redox reaction, because what do we end up forming? An ionic compound, right? Here we had sodium atoms. Here we have sodium ions. Here we have chlorine, a chlorine molecule that has 2 atoms. And here we have a chloride ion. For them to form ions, there was a transfer of electrons. So in both of these reactions, we have a metal reacting with a nonmetal. And we see the metal forming a positive ion in both cases, the nonmetal forming a negative ion. So we've got a conversion of free elements into ions. Redox reaction. Yeah, I kind of already said most of this. So we have to have electrons being gained or lost. Electrons, a little bit like the proton, which is the hydrogen ion, just a single subatomic particles. These are not found just roaming about by themselves. If one atom loses electrons, another atom has to accept them. And there's no electron bank that you can just go and make a withdrawal on. If an atom is going to gain electrons, they have to come from another atom. So if one atom loses, another atom must accept them. So we say that atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. These terms came from the description of this process in organic chemistry, where the words make more sense, because oxidation means that it's gaining oxygen. That doesn't work so well in inorganic chemistry, which is what we're studying right now. So this is how we remember which one is which, because we have another example of we have two pairs of concepts and we have to figure out how they go together. So we remember oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So here we've got the sodium to go from sodium atom to sodium ion. It loses an electron. Oxidation is loss of electrons. Here the chlorine is gaining electrons. Reduction is gain of electrons. And this is something that unless you use, you're looking at redox reactions a lot, it just really doesn't stick in your brain. And I have to be real careful because I can get them backwards too. And so I think oil rig in my head a lot. It's just very useful. Now, in order for a reaction to qualify as an oxidation-reduction reaction, we don't have to have a complete transfer of electrons. We don't have to have actual ions forming. So let's look at this example. We've got hydrogen gas and chlorine gas, and they react to form. How would we name this? It's a gas. It's not aqueous. Do we name this as an acid? No. We name it, yes, hydrogen chloride. We name it as a binary molecular compound. Two nonmetals, you name the first element first, you name the second element second. Now this is an example where we don't use mono on the second element. Sorry, it's kind of an exception. It's hydrogen chloride. Although if you called it hydrogen monochloride, we would definitely understand what you mean. Here we have an illustration of a hydrogen molecule. The hydrogen molecule is two hydrogen atoms and they're sharing electrons between them. The chlorine molecule, electrons are being shared. What happens when the reaction occurs and we've got the hydrogen and the chlorine forming a molecule? Chlorine is an electron hog. They are sharing electrons, but they're not sharing very equally. This is like the older brother. Now, Andrew's too old for this. He's 5. He recognizes when you're not splitting the cookie in half exactly equally. But when he was 1, you could share a cookie with him by giving him like a fourth of it, right? Here, I'll share the cookie with you, and I get more of it. I'm sharing, Tommy says. I shared with him. Yeah, but you didn't share equally, right? So that's what happens with some combinations of elements. The chloride is greedy, and it hogs the electrons. So there is a partial transfer of electrons from the hydrogen to the chlorine. It's not complete. It doesn't actually form an ion in the gas state. It's a partial. So this uneven sharing increases the electron density for chlorine and decreases the electron density for hydrogen. So chlorine had a gain. Reduction is gain of electrons, or gain of part of an electron. Oxidation is loss of a whole electron or part of an electron. So the hydrogen is oxidized and the chlorine is reduced. Any questions? No, it seems a little weird. When we get redox reactions between nonmetals like hydrogen and chlorine, those are a lot harder to identify than combustion. Combustion's easy because one of the reactants is oxygen. And when ions are formed, those are easy to spot. So we use what's called oxidation states or oxidation numbers as a way of tracking electrons before and after a chemical reaction to help us identify, is this a redox reaction or not? Now, it's really important to remember, oxidation states are not the same as ion charges. This is an imaginary thing that we have created to help us understand what's going on. These atoms themselves have no idea that we're giving them oxidation numbers. It's kind of like, maybe the guys in high school and didn't know that the cheerleaders were secretly ranking them, right? Okay? This is just something that's made up. It is not an ion charge. Ion charges are real and measurable. Oxidation states are completely made up. But we need to learn how to play the oxidation state game. So these are the rules. Anytime you have a free element, an element by itself, whether it's diatomic or monatomic, that oxidation state is 0. So sodium, the element, 0. Chlorine, 0. So when we have these reactants, 2 sodiums plus 1 chlorine molecule, they're just elements, their state 0. If you have a monatomic ion, like sodium, in sodium chloride, we would say the sodium has a +1 oxidation state and the chloride has a -1, because they are ions. If it's an ion, its oxidation state is the same as its charge. Okay? The sum of oxidation states of all of the atoms in a compound is 0. So here, sodium chloride, that overall has no charge, right? And so we have a sodium ion that has a +1 oxidation state, and we have chloride with a -1 oxidation state, and those add up to 0. So the oxidation states coincide with ion charges, right? But they are not the same. So they overlap sometimes, but we can't extend that into places where they do not overlap. Third, oh, I didn't number that very well, did I? Yeah, okay. Let's just fix that. Because PowerPoint does not continue numbering onto the next page very well. So that's 4, and this is 5. That bothers me. The sum of the oxidation states of all atoms in a neutral molecule is 0. If you have a polyatomic ion, the sum of the charges equals the charge on the ion. So if we look at NO3-, the nitrate ion, this is an ion. It has an overall -1 charge. The sum of all the oxidation numbers of these atoms in here has to equal this -1 charge. And we haven't told you yet why nitrogen would be +5 and oxygen would be -2 in there. We're telling you this is what they are, and oh look, they add up to -1. In their compounds, metals are going to have positive oxidation states. Group 1 metals always have an oxidation state of +1. Group 2 is always +2. This is kind of redundant because this is the same as we said in an ionic compound. The charge and the oxidation state are the same. So I don't know why this is in here twice. And this is actually rule number 6. The nonmetals. The nonmetals are the tricky ones in compounds. And so we have this table. So fluorine is going to be -1, hydrogen is going to be +1, oxygen is going to be -2. The group 7As are going to be -1, the group 6As -2, the group 5As -3. Is this related to something we've learned earlier? It is, right? So here we're saying that the oxidation number of these nonmetals is going to be equal to the charge that they would have if they were in an ionic compound, right? If they formed an ion, what charge would they have? That's the oxidation number. Now, the slightly tricky thing about this is sometimes in a compound you'll have conflicting things. And so this is a hierarchy, and the top one takes precedence. So if you have a conflict between fluorine and another group 7A element, fluorine wins. So how could that happen? Well, what if you had this compound? That looks like a weird compound, but it can exist. If you just look at what charge these elements would have if they formed ions, this would be -1 and that would be -1. But that's not going to work because this is a neutral molecule and the charges, the oxidation states have to add up to 0. So how do we decide who gets the -1? The other one's going to have to be +1. It's this list. Fluorine, hydrogen, oxygen, and then 7, 6, 5. Okay, so you have to find a way to remember that. So in this compound, we would give fluorine a -1 oxidation state, and we would give chlorine a +1 oxidation state. Isn't this a fun game? We're just full of fun games, aren't we? Not. So hydrogen in the compound water, we give hydrogen a +1 oxidation state. For oxygen and carbon dioxide, each of these oxygens is going to have a -2. In carbon tetrachloride, chlorine is group 7A, that's going to be a -1. Here in this one, group 5A, nitrogen gets a -3 state. This is not conflicting with the oxidation state of hydrogen, though, because hydrogen has what oxidation state? +1. So the hydrogen has +1, the nitrogen has -3, and because there's 3 of those hydrogens, it all works out together. There's no conflict between those two elements. Let's do some examples. Why was nitrogen 5 in that previous slide? Yeah. Okay, that's a very good question. So let's look at this guy. Oops, I can't do that. So nitrate. Let's see, there's just not much room in here. So let's look at nitrate. So from the rules, the first one was fluorine, hydrogen, oxygen. So the oxygen is going to have a -2 state, right? And there's 3 of them. So that gives us oxidation states of -6. This has a -1 charge. The oxidation states have to add up to -1. If we've got -6, there's 1 nitrogen in there, it must be +5. Going further down this table would say that nitrogen in group 5A should be -3, but oxygen takes precedence. So we do the oxygen, and the nitrogen has to be what's ever left over. There is a reason for this order. There's a reason for the order, but it's actually easier to just remember the order.
Does it have to do with electronegativity?
It does have to do with electronegativity, and I think some other factors as well. Nitrogen is more able to have a positive charge than oxygen is. And just to add more fun to the mix, you can end up with fractional oxidation states. For oxidation states, we're going to write the sign before the number. The sign, I'll just read it. The sign is written before the number for oxidation states and after the number for ionic charges, just to help us mentally separate those. Oxidation state is not the same as ionic charge. even though they happen to be the same number sometimes. Okay? Okay, let's determine the oxidation number of each element in these species. So, zinc chloride. Well, before we can determine an oxidation number, we have to have a formula, right? What kind of a compound is this? It's ionic. So we're going to look for the ionic charges to figure out what the formula is. What's the charge on zinc ion? 2 plus. So zinc, 2 plus, and chloride, minus. And so when we put those two together, we're going to get a formula of ZnCl2. This is an ionic compound. In an ionic compound, the oxidation numbers are the same as the ionic charges. So for zinc, the oxidation number is +2, and for chloride, it's -1. Everybody okay with that? Sulfur trioxide. What's the formula for the compound? SO3. This is 2 nonmetals. It's one of those binary molecular compounds, which the tri in here is a dead giveaway. So tri says there's 3 oxygens, and there's 1 sulfur because there's no prefix in front of that. So here we have 2 nonmetals. We can't think about charges here. So we have that table in our mind. Fluorine, hydrogen, oxygen. Oxygen always gets -2. So the oxygen is going to have an oxidation number of -2. We figure out what the sulfur is from the oxidation number of the oxygen. So here we've got 3 oxygens, and they each have an oxidation number of -2. So that gives us a total of -6, right? This is like figuring out charges on ions, but these aren't charges. So that's -6, and these have to add up to 0, so the sulfur must be +6. Well, in a reaction, what we're going to find is we're going to look at the change in oxidation numbers to determine if oxidation or reduction has occurred. So it hasn't actually lost 6 electrons, but it is short of electrons in this compound. And this is something that you probably have not heard about before. They don't usually go over this in high school, and they don't teach it in Chem 3A either. So this is probably brand new. It's going to be kind of strange. Okay, nitric acid. HNO3. This is not hydronitric acid or something. If it had a hydro, it would just be hydrogen and nitrogen. Nitric acid, so there's no hydro in front, that tells us this is an oxyacid. So nitric is related to nitrate, NO3 -1, and so we put the hydrogen on there to balance the -1 charge, and we get nitric acid. So we use the charges to figure out what the formula is, but this is not really an ionic compound, and we have a polyatomic ion here. And anytime you have a polyatomic ion, things get a little interesting. So here we have 3 elements, so we need, and they're all nonmetals, so we need to go down our table. What's first? Of these, hydrogen is first. The table went fluorine, hydrogen, and hydrogen gets what oxidation number? +1. After hydrogen was oxygen, and oxygen gets -2. And next will be the nitrogen. So now we have to look, what should nitrogen have so that the other ones have what they want? It's a little bit like, my kids have places they want to sit in the van. And of course, everybody wants to sit shotgun, right? And so you get this conflict. There's a pecking order. The oldest kid gets shotgun, right? So if it's Tommy and Emily, Tommy gets shotgun. But if it's Emily and Andrew, Emily can get shotgun. And so that list is sort of like a pecking order. Fluorine gets first choice, he wants -1. Hydrogen is next, he wants +2, then oxygen. If you have a conflict between those two, they can't have what they want, the one that's higher on the list gets what it wants. Okay, so we went through that order, and now we have to figure out what nitrogen is. Well, 3 oxygens would give us -6, and the 1 hydrogen is +1, so that gives us a total of -5. And what do all of these oxidation numbers have to add up to for nitric acid? 0. So nitrogen must be +5. Is it starting to make a little sense? I see some concerned looks. Yeah. This is kind of a middling deal. This is not a huge deal. You could pass the class if you don't get this, but don't give up on it yet, okay? How about dichromate ion? Cr2O7. And what's the charge? 2-. Really close. When you're doing things like this, like in the homework and stuff, try to do it without looking it up first. You'll learn more that way. Try to do it without looking it up, and then, yeah, go check it. Make sure you got it right. Okay, so here we've got 2 elements. We've got chromium and we've got oxygen. This is a polyatomic ion. This is not an ionic compound. Okay, so we're not going to look for what charge does the chromium ion take. We're going to go to our pecking order, and oxygen gets its first choice, which is -2. The oxygen is -2. The chromium is going to be whatever else works so that this ion gets the right charge. So we've got 7 oxygens. So their oxidation numbers add up to -14, right? And overall, we have a -2 charge. So we could do it like this. We have -14 plus something from the chromium, and it's going to add up to -2. What goes in this blank? 12, right? So that tells us the combined oxidation numbers of these 2 chromiums plus 12. So we divide it by 2, and each chromium must be +6. So you work through it that way, and then it's a good idea to check and make sure that that actually works out. So you look at this, okay, 2 times +6 is 12, and this is -14, and yeah, that adds up to -2. We're okay. Any questions? So we can use these oxidation states or oxidation numbers to identify redox reactions that are not obvious. So oxidation, we said oxidation is loss of electrons. Okay? When you lose electrons, your oxidation state goes more positive, right? Reduction is gain of electrons. That causes a decrease in your oxidation state. Okay? So if we look at this example, here we've got the element carbon reacting with the element sulfur. Both of these have oxidation states of 0. In this compound, carbon disulfide, in the pecking order was fluorine, hydrogen, oxygen, 7, 6, 5, right? Well, sulfur is in group 6, carbon's in group 4. He didn't even make it on the list. So sulfur gets -2, which happens to be the charge it would have if it was in an ionic compound. So the sulfur gets -2. There's 2 of them, so that would be a total -4 oxidation state. And it has to add up to 0, and so we figure out that carbon has +4. So we identify the oxidation numbers or oxidation states of each element in each compound. And then we look and see, has it changed? Has the oxidation of carbon changed from reactants to products? And yes, it did. The oxidation number went up. If it goes more positive, that means it loses electrons. Oxidation is loss of electrons. So the carbon is oxidized. If something gets oxidized, there must be something else that gets reduced. Here we see the sulfur goes from 0 to -2. It had a decrease in oxidation number. You go lower, you go more negative by gaining electrons. Reduction is gain of electrons. The sulfur was reduced. That's the thought process that goes on behind looking at these. Questions? So the oxidation reduction must occur simultaneously, because if one atom loses electrons, another has to gain them. Even if it's a partial transfer, not a complete transfer. So the reactant that reduces an element is called the reducing agent. And this is very confusing, because the reducing agent becomes oxidized. Well, let's think about this. Let's think about models and actors. They have agents, right? Do the agents do the acting? No. They're just an agent for the actor to get a job. The agent doesn't do it, he just arranges it. Okay? So the reducing agent is not reduced, it arranges for somebody else to be reduced. If he's not reduced and somebody else is getting reduced, the reducing agent must be getting oxidized. That's how I think about it. The reactant that oxidizes another element is called the oxidizing agent. The oxidizing agent becomes reduced. This one is so easy to get backwards. Let's look at some examples here. Use oxidation states to decide whether each of the following is a redox reaction. Okay, so in the first one, we need to look at the oxidation states of the reactants. What's the oxidation state of sodium?
0.
0. It's an element. And how about chlorine?
0.
0. It's an element. And in the products, the sodium has what oxidation number? +1. And the chloride has -1. How do we know that? This is an ionic compound. In an ionic compound, the charges of monatomic ions are the oxidation number of that atom. So, is there oxidation reduction occurring here? Yes. One element went up in oxidation number and one went down. So what is happening to this sodium? Being oxidized or reduced? It's being oxidized. Oxidation is loss of electrons. The oxidation number went up because it would have lost an electron. So this is being oxidized. And the chlorine then must be being reduced, right? Okay. Which of these is the oxidizing agent? The chlorine is the oxidizing agent. It causes the other one to be oxidized. It doesn't get oxidized itself. It's the agent for that to happen. Chlorine is the oxidizing agent. Sodium is the reducing agent. Okay? Let's do another example. So here we have, and that first one, we could look at that. We've got a metal and a nonmetal forming an ionic compound. You don't really need oxidation numbers to tell you that that's a redox reaction. You can see that ions are being formed from atoms. But this one is not so obvious. So here we have calcium oxide, carbon dioxide, making calcium carbonate. So this compound is an ionic compound, and so the oxidation numbers of these two monatomic ions will be equal to the charges on their ions. So the calcium is going to be +2, and the oxygen is going to be -2. It's an ionic compound. Carbon dioxide, here we have two nonmetals. We have to use the table in the pecking order. So fluorine, none of that. Hydrogen, none of that. Oxygen gets -2. The oxidation numbers have to add up to 0 for carbon dioxide because it has no overall charge. We've got 2 of these -2 oxidation numbers, and we have a carbon, and so he must have an oxidation number of +4. And then we go over to calcium carbonate. This is an ionic compound. This is a monatomic ion, so its charge is the same as its oxidation state is the same as its charge, so that's still +2. This, though, is a polyatomic ion. It's got more than one element in it. So we can't just say, oh, its charge is the same as the oxidation number is -2. Because there's 4 different atoms in there. So we have to look at these nonmetals. Oxygen wins again. Oxygen gets to be -2. He gets to ride shotgun. There's 3 oxygens, a total of -6. And you can either think of this, we could think of this as an ion, a polyatomic ion separately, or we can think of the whole molecule together. Which one do you want to do? Whole molecule or polyatomic ion? Together, okay. So this is a compound with no overall charge. All of the oxidation numbers have to add up to 0. So we've got +2 from the 1 calcium, and here we've got 3 oxygens, that's -6. So far we have +2, -6, we've got a total of -4, right? And we have 1 carbon in here, so he must be +4, right? One of these plus 1 of those plus 3 of these is going to add up to 0. So now we can look at these and see if there's anything changing and identify if it's a redox reaction or not. Does the calcium change its oxidation number? No. Does the carbon change its oxidation number? No. How about oxygen? Here it is in 2 places. Over there it's -2, and over here it's -2. This is not a redox reaction. There's no transferring of electrons at all going on here. And the best way to figure that out is looking at these oxidation numbers. It's a device we've created to help us identify things like this. Any questions about that one? Okay, let's look at this last one. So think about it. What's the oxidation number on the potassium? +1. How about on the oxygen? -2. What about the nitrogen? Let's see, -6, we have +5. Okay, we get the nitrogen by looking at the other ones. We've got +1 from the potassium, and minus a total of 6 from the oxygen. That adds up to -5. We know that overall it has to be 0, so the nitrogen has to be +5. This coefficient of 4 plays absolutely no part in determining oxidation numbers. How about over here with the K2O? What's the K? +1 and the oxygen -2. That's an ionic compound. We have 2 monatomic ions. Oxidation number is the same as the charge. How about nitrogen?
0.
0. It's an element. Oxygen?
0.
0. Okay, so is there any oxidation reduction occurring here? Yeah. What's changing? The nitrogen. It started out as a +5 and it ends up as a 0. What else is changing? Oxygen. Some of the oxygen is changing from -2 to 0. Some of the oxygen is staying the same. That's okay. So this is a redox reaction. Which element is the oxidizing agent? I'm going to think this out loud. The oxidizing agent is reduced, right? The oxidizing agent is reduced. Reduction is gain of electrons. If you gain electrons, your oxidation number goes down. So then I look for which one had an oxidation number that went down. It would be the nitrogen. So nitrogen is the reducing agent. No, I said oxidizing agent. What did I say? I started with oxidizing agent. Yes, I'm sorry. This is confusing. See, I don't use this much because I don't teach 1A very often. And so I have to think about this. And so I understand this is challenging. So that was the oxidizing agent. Because the oxidizing agent was reduced. And so then what is the reducing agent? Oxygen. So the oxygen is the reducing agent. The reducing agent causes the other thing to be reduced. The reducing agent gets oxidized. Oxidation is loss of electrons. If you lose electrons, your oxidation number becomes more positive, right? Some of the oxygen went from -2 to 0, which is more positive. Okay? It takes a long time before looking at something like this becomes just really automatic. But I just run through those thoughts in my head. So, if I'm looking at that, which one's the oxidizing agent, there's going to be a pause while I run through those concepts. And so, yeah, that takes time, but it works every time. And you don't have to do this that often, so that's what I recommend to you, is just think through those steps like that. Because you could have questions about this, which element is being oxidized, which element is the oxidizing agent, is this a redox reaction? There's a number of different questions that could be asked. What's the oxidation number of potassium in the product? All kinds of different questions. Do you have any questions? Combustion reactions are generally oxidation-reduction reactions. They are characterized by the reaction of something with oxygen to form oxygen-containing compounds. Often these include water, and combustion reactions also emit heat, which we could remember that because when you burn something it gets hot, right? Here's an example, natural gas, which is methane, reacting with oxygen. When we have a hydrocarbon, this is a hydrocarbon, right? It's just got carbon and hydrogens. anytime you have a hydrocarbon combusting, the products are the same. Isn't that nice? Carbon dioxide and water. So we can look at the oxidation numbers here. This is two nonmetals. So hydrogen is second in the pecking order. He's way above carbon, which didn't even make the list. So hydrogen gets to be -1. That makes the carbon +4. What? I'm sorry. That's right. My thinking's wrong. Hydrogen is not -1. Hydrogen is +1. Okay. Hydrogen is second, but hydrogen wants to be +1. He doesn't want to be -1. Good grief. He gets to be +1. And then the carbon must be -4. Here's oxygen, the element, 0. Over here we've got carbon dioxide. Oxygen gets to be what it wants, which is -2. And therefore the carbon has to be +4. In water, hydrogen trumps the oxygen, although oxygen still ends up getting what it wants. But we do the hydrogen first, he's +1, and the oxygen ends up being -2. And so we look at this, and what's changing? The carbon. The carbon went from -4 to +4, and the oxygen went from 0 to -2. Which element is being oxidized? Oxidation is loss of electrons. When you lose electrons, you become more positive in your oxidation state. So the carbon is being oxidized. That means that the oxygen is being reduced. Okay, so we see this in all combustion reactions. So the shortcut is something reacting with oxygen to form oxygen-containing compounds. Combustion reaction, you can just say, yeah, that's oxidation reduction. Here's another example, ethanol, which is the alcohol that's in alcoholic beverages, will burn. So here's ethanol. It reacts with oxygen. This is a hydrocarbon. It contains oxygen, but it's also going to form CO2 and water. Let's write the balanced equation for the combustion of benzene. So here's benzene. You're not expected to know why its name is what it is. If this is a combustion reaction, what's the other reactant? Oxygen. And what are the products? Carbon dioxide and water. We know the other reactant is oxygen because we memorize that. We know that the products are CO2 and water because we memorize that. We remember it. Now we have to balance it. Oxygen is by itself, so we're going to leave him for last. So let's look at the carbons. There's 6 here. I need a 6 over here. There are 6 hydrogens, and over here there are 2, so I need to put a 3 there. And now we're going to look at the oxygens. Over here on the right side I've got 12 oxygens plus 3 oxygens, and that is 15 oxygens. And on the left I see that I can only buy oxygens in pairs, but I need an odd number of them. So this is what I call the odd-even problem. There's 2 solutions for this. You can use fractions, or you can just double everything. Because when you double an odd number, it becomes an even number, right? Problem solved. That's the one that most students like, because a lot of students, like my middle school math teacher friend says, a lot of students feel that fractions are the F word, right? So let's just double this. We see we've got an odd-even problem. So we were working on this guy, so we're going to leave him alone, but we're going to double everything else. So I'm going to put a 2 here. I'm going to change this to 12. I'm going to change that to 6. Now I've got 24 oxygens. Yes, it seems like a lot, but it's okay. And I have 6 oxygens, and that adds up to 30. which is divisible by 2, and so I can put a 15 over here, and there I'm good to go. The other option, instead of doubling everything, is to put a fractional coefficient of 15 halves, because 15 halves times 2 is 15 and gets you that odd number of oxygens. But then you have to go through and clear that fraction by multiplying everything by 2. So I think just doubling everything kind of saves a little bit of time. And most students find it's conceptually easier to understand. Any questions? That odd-even problem comes up a lot in these combustion reactions and drives some students absolutely bananas. I'm looking at this problem and I'm thinking, why is this in this section? So we would have to write a chemical reaction, but they're giving us the products and the reactants. This is a stoichiometry problem. We're not going to do this right now. Haven't we had enough of chapter 4? I think so. Oh, look, we're done.